Okay, next topic then, exact volume. So we see that we can do these approximate ones with Riemann sums. They're not hard, they're just tedious, and which tedious is great for computers and calculators to do. But now we want to switch and go to exact volume. And just like in R2 over here, we can make things exact if we do this limiting process. So to find the exact volume of this, we're going to have integrals, but instead of a single integral like we did over here, we're now going to have a double integral. So this will be done with a double integral over your function for a small change in the area. And so for us, this is going to, and over your region R. So again, R was just this square, special type of rectangle in the XY plane. And so for us, this then becomes the square root of xy. And then we're going to talk about how we got dy dx, but, oh, sorry, all this time I had that as an x, that should be a y. Y goes from 0 to 1, and then you always, we're going to do something, this is called an iterated integral, which we work from the inside out. And so we really think about doing that integral first, and then the last one is x goes from 0 to 1. Right. So had the region changed, so this is one example, and then maybe down here, it was under same function, z equals square root of xy over r equals, sometimes they write it like this, 0 to 1 on x cross 0 to 2 on y. These are your x's, these are your y's. So now this is a rectangular, actual proper rectangular region. 0 to 1, 0 to 2. In that case, the exact volume would be exactly double integral square root xy. Y goes from 0 to 2. X goes from 0 to 1. So again, they go work, this y goes with these limits, and it might help in the beginning to label them, that those are y equals limits and these are x equals limits. Same thing here. X was the outer one, so these are x equals, these are y equals. And especially when we ultimately get to triple integrals, right? We could extend this, many things, just keep extending, extending. So we could do triple integrals, in which case we've got x's and y's and z's. It really helps then to kind of have these labels so you can keep in mind, am I integrating this thing with respect to x or y or z? Okay, so this does represent the exact volume of the problem that we want. And now I just have to tell you how to do a couple of these. And so the derivation, but I think you got it from the approximate as n goes to infinity. It's this page here, exact volume. So we're really doing a limit of a double sum, right? Because we can change in the x direction and in the y direction. We have a two-dimensional thing in the xy plane, a region R in the xy plane, creates the double sum. And if I take that limit as both n and m go to infinity, I get the double integral here. Now this double integral, again, is worked as an iterated integral from the inside out. So let's actually do the volume for Chiche's. Go ahead and complete this, then we'll do this modified problem. I'm going to do a couple others so we can practice doing double integrals. All right, so square root of xy, dy, dx. It's going to help us if we get rid of the square root. Well, that's really x to the 1/2 times y to the 1/2. Again, I'm going to work it from the inside out. These were y limits. So just like you do partial differentiation, partial integration is the same. You treat, in this case, I'm integrating with respect to y. That's the variable. Everything else is a constant. So I just need to integrate, here's a constant, this is just like integrating, 7y to the 1/2. So I just really have to integrate the y to the 1/2 and multiply by this constant, which isn't 7, but it's x to the 1/2. Okay, so when I do the integration, I haven't done anything with the outer integral, so I'm just going to copy that. And then I'm going to go ahead and put in this bracket the antiderivative of this part with respect to y. So I really just take y up a power over the power. So that becomes y to the 3/2 times 2/3 times this constant. So y to the 3/2 over 3/2 is the same as multiplying by 2/3. 2/3 times the x to the 1/2. That is the antiderivative with respect to y, but now I need to evaluate it because it's a definite integral at my y limits. Y goes from 0 to 1. So I plug in at the upper limit minus what happens at the lower limit. I haven't actually done this integral, so again, I'm going to carry that along one more time. And in this bracket, I'm going to go ahead and do the evaluation. So when I plug in y, 1 to the 3/2 is 1, times 2/3 x to the 1/2. That still just stays 2/3 x to the 1/2. Minus what happens at the lower limit. When I plug in 0, 0 to the 3/2 is 0, 0 times anything is 0, a big 0 back there. All right, so now I need to integrate this with respect to x. Now it looks like an R2 problem, and that should happen as you start working your way out from the iterated integral. You should eventually get to just an R2 type problem. Definite integral, so I should get a number when I'm done. That number, though, instead of representing an area, it represents a volume because it was a double integral. Okay, so let's clean this up a little bit. All right, so I just need to integrate this with respect to x. Nice power rule, up a power over the power, so x to the 3/2 over 3/2 is x to the 3/2 times 2/3, so times another 2/3, 4/9 x to the 3/2, evaluated from 0 to 1. I can just say 0 to 1, or again, I want to just remind myself it's not as confusing at this point because x is the only thing left, but I'm plugging in for x. Plug in at the upper limit first by the fundamental theorem of calculus, so I'll have 1 times 4/9 minus 0, so just 4/9, which is, oh, that's the 0.44, right? Just keeps on repeating. So think back to the previous video with the tech tool. We used calcplot3d to approximate this, and we were getting, I think when we had n equals 20 in each dimension, so n was like 400, we'd use 400 rectangles, and we had like 0.445. So we were getting there, but we only had 2 decimal places of accuracy at that point. Just like over here, the bigger the n, yeah, it's more work, it's more tedious, but you do get a better and better approximation. You can figure out how close to your approximation. There's whole things you did back here with error analysis. You could do something similar here. But because the DAC volume is so easy, we often just jump right to that. When would you need the approximate volume? Well, let's think about our integrals here. Are there instances for which you can't get an antiderivative? Yeah, remember the classic function from an earlier class, could have been Calc 1, e to the minus x squared has no antiderivative. And that's that normal function. Well, it's used so often, and yet, we don't have an explicit closed form representation of that. So you can always use approximations. Those are great instances where you could use. Another instance where your integral is just terribly messy and nasty. There's no sense in trying to crank out by hand antiderivatives during this integration when you can just go right to a tech tool and get any desired degree of accuracy that you like, as long as you have enough time, enough computational power. Okay, so that was Chi-Chi's sleeping bag over this region, but let's try it over, we picked a different rectangular region where we just went, y was from 0 to 2. Not much is going to change. We won't finish this because it's a pretty easy integration, but let's just set up the picture and set up the integral. It would go from 2 here to 1. The region's bigger. It doesn't necessarily mean the volume doubles because the surface is nonlinear over top of that. So the only thing that would change is y goes from 0 to 2. Okay, and you could take it from there. That'd be a good one to practice. Do it by hand and then do it in a tech tool. But you might have a question, you know, why did I put dy dx? What if I had done this integral, and is this the same thing? Same function, square root of xy. Say I did dx dy this time. This means these are x equals limits, and the outer ones are y equals limits. So this time x goes from 0 to 1, 0 to 2. Is that going to be the same thing? There's a neat theorem. So where are we in your book here? Yeah, okay, so this is the page shortcut for double integrals up here at the top. You can switch the order of integration when your limits of integration are constants. So if you're always integrating over a rectangular region, no problem. You can actually switch the limits of integration and nothing's going to change. Now, hopefully it makes sense why that's okay, because we're eventually going to get to things like a region, maybe same function, TJ sleeping bag, but it really looked more like this, didn't it? Like, sort of had this front face, so maybe it was this triangular region. So we're going to have to figure out how do we actually define that in terms of our x's and y's. X goes from 0 to 1, y goes from 0 up to this line, which is the line what? 1 minus x, yeah. So we can say 0 less than equal to x, less than equal to 1, 0 less than equal to y, less than equal to 1 minus x. Now you see that these are not constants. Y would have limits of integration. If we did dy dx, if we did y first, y would go from 0 to 1 minus x. So it depends on x. They are not all constant. You can't just switch easily. You can't just write. It takes a little more effort and thought to think about what x is going to go from. You can't do this. And hopefully you see why maybe just algebraically from this representation is you're going to end at the end with something that has x's in it, right? You're not going to get a number or constant that would represent a volume. And so these are not equal, these two things. We'll learn how to do this. You can switch the order of integration, and that'll be next week in the module. So for now, it's just important to recognize when your region is rectangular, you're free to switch the order of integration, no problem. You'll have no issues. So if it's not though, you're gonna have to think a little bit, wait, and we'll learn more next time. So that's one useful piece. And then the other useful piece of information is also on that same page. That's the box below it. This is a neat theorem by Guido Fubini, Italian mathematician. And he says that if your f of xy function is something called separable, which means it can be written as a function of x times a function of y. So they're not having any interaction terms. Then you can separate it and do two single integrals. So you can turn a double integral into the product of two single integrals. So that's a really useful one as well. And there's a problem just below that that shows that example, and then I'll pick a few other problems to work here. So I'm going to work a few more exact volumes by hand, a couple more double integrals. Pick a couple from your journal here. Okay. Okay, they asked you to compute this double integral. They didn't really set it up that there was a, there's really though when you're doing a double integral, just like over here, every time you're doing a single integral, there's a picture in your head that can go with it because every single integral represents an area whether or not it was meant to be that way. It might be an arc length. What else did we do with those? Average values, all sorts of things that you do back here, but really there's always a picture anytime you see a single integral. Same thing with the double integral. There's always a picture that goes with that. And what we're trying to get now is a volume over this region in the xy plane. 1, 2, 3, minus 1 to 2. Oh, that's another square as well. Over that surface, it's not a paraboloid, it's not a hyperboloid. So anyway, we could get a contour map to take a look at that if we want to visualize it, but there's some surface that lives above and possibly even below this, and we want to get the volume of the region that goes from this surface to this region in the xy plane. Okay, so first thing we notice is that this is a rectangular region, so no problems deciding which way to do this dA. We can do it dx dy, dy dx, but when we do it, we just have to make sure either way we pick, like if I say dy dx, these inner limits must be y ones, right? This would be minus 1 to 2. I just have to make sure they correspond, working my way inside out. Now we have an iterated integral. We can do it from the inside out, integrating with respect to y. I haven't done anything with the x's, so I'm going to leave that. Here in this bracket, I'm going to put the antiderivative with respect to y of 3x squared minus 2y. 3x squared is a constant when y looks at it, so when it integrates that, it'll get 3x squared times y. Minus, this is just a y term, no problem. Minus 2y squared over 2 is y squared. Evaluate at the upper limit, minus what happens at the lower limit. Integral from 0 to 3. Let's see, 3x squared times 2, so 6x squared, minus 4. Minus what happens at the lower limit. And then that's going to be dx. So at the lower limit, when I plug in minus 1, I'll get minus 3x squared. Minus what happens with minus 1 squared, so that would be minus 1. We can do a little bit of cleaning up before we do the integration, the last bit of integration. So I have how many x squareds? That's going to be 9x squareds. How many constants? We got a plus 1, so minus 3. I want to integrate this now when x goes from 0 to 3. Nine x cubed over 3 is 3x cubed minus 3x, evaluated from 0 to 3. Let's see, that's going to be 3 to the 4th is 81, minus 9, minus 0, minus 0. So what is that, 72? So that's saying that the volume under this surface, so you could check this by graphing z equals 3x squared minus 2y. Go to calc plot 3D. Graph this over this region. Check that the volume, the exact volume is 72. You have a way to get it approximately with increasing the number of rectangles and see how good it is. But you can also just check that is it this surface above, or the majority of it above the xy plane over this region. Okay, let's do maybe one more here. All right, this says compute the volume from z equals xy e to the x to the region R which is 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 2. All right, again, we're starting off with nice simple regions R. It's easy to see that R is just a rectangular region. No problem. So that means I can, it doesn't matter the order of integration, I can do dy dx, dx dy. It'll give me the same answer. So the volume is exactly equal to this double integral, which really represents the limit of a double Riemann sum of x, y, e to the x. Let's say I wrote it as dx dy. Maybe that's the way I want to do it. That means the inside are x limits 0 to 1. The outside are y limits 0 to 2. But when I look at this now and I start to take the integral, what do you notice because I'm working from the inside out? I'm looking at this with respect to x and I want to integrate it. What kind of rule am I going to need? Well, I see that I have an x, and then there's the constant, e to the x. So it's really like trying to integrate x e to the x. That's the essence of this one. And so in this case, x e to the x requires which rule for integration? If I was taking the derivative, it would be the product rule, right? And that should be your clue that this is probably integration by parts. So a good bit of work if I want to do a dx dy. But hopefully you know, just by that I can switch, but hopefully you see right away by switching and doing this as a dy, x, y, same function, e to the x, so that hasn't changed, hasn't gotten any different. But when I switch to dy dx, just looking at the indefinite integral, hopefully you see now that the dy dx is much, much easier to integrate. So hopefully that's going to help us when I'm working from the inside out. If I can make it easier on the inside, that always helps. So integrating with respect to y means I need to make sure I put my y limits. Y goes from 0 to 2. X goes from 0 to 1, right? Same thing, we worked another problem where it was equally easy, whether I did dy dx or dx dy. Here's an instance where you definitely want to switch the order of integration. It's going to make it much easier. Again, we're allowed to do that because the region over which we're working is constant. Constant limits of integration of the region is rectangular. Okay, so I integrate this now with respect to y, working from the inside out of this iterated integral. With respect to y, this x and e to the x, they're just constants, no problem. So I just need to integrate y. That'll be y squared over 2 times this special xe constant. And then I need to evaluate that y goes from 0 to 2. And don't forget, you still haven't done anything with the x's, so make sure you just carry those along. X goes from 0 to 1. Okay. Evaluate at the upper limit, just reminding yourself there's lots of letters so you don't get confused. I'm plugging in for y now. So I plug in 2, and I'm going to have 2 squared is 4 divided by 2 is so 2 times x e to the x. Next, y equals 0 goes away, dx, integral 0 to 1 dx. Oh, and that actually didn't help us now. We still have that, we're still facing this, what would be a product rule by differentiation is a integration by parts here. You can pull out a table. There's a common ones in the back of the book for tables, or you can just go back to your usual tech tools. So yes, this is a single integral. I don't think I've shown these, so let's just share quickly. All right, so let's go to Wolfram Alpha, and let's just do integrate. Okay, so some preset ones that you can check out and then just modify the, use that as for your template. We want to do 2x e to the x dx from x goes from 0 to 1. All right, so single integrals, you've probably seen these already. Evaluates the 2. So the volume of this surface over this rectangular region, it either entirely or a majority of it lies above the xy plane because we get a positive value for the volume. It's possible you can get negative values for the volume if your surface largely lies either entirely below the xy plane or partially. Okay, so, but that really wasn't the main point. I want to show you the TeX tool, Wolfram Alpha, can do double integrals as well. The syntax can get a little tougher to enter, so let's just go to the double integral calculator. Okay, so it shows, here's a function, you can put in your variables, but we have a definite double integral. So we want to enter values for the domain, for the limits. Basically, it's letting you enter your limits. Okay, so we could have started not working this by hand, we could have started from the very beginning and just entered the problem as we modeled it, which is xy e to the x. Now here's what I think is a little bit confusing. So I usually put it in one way and then check visually what Wolfram does. So say we wanted x to go, we had it set up originally as dx dy first, and so x went from 0 to 1. So x 0 to 1, y went from 0 to 2. And then when I'm just checking on, I don't know when it says variable 1 or variable 2, whether that means inside or outside, I always forget. Okay, so just check that it is in the right form. It shows the definite integral here. xy e to the x, that was correct what we had. It's showing dy dx, so that was actually this part, the second way we set it up. So variable 2 is your inner one, I guess it's saying. And just make sure that that's what you wanted. Y goes from 0 to 2, x goes from 0 to 1, it gets a value of 0. Now those were all constants. Again, at this point, we're just doing constant limits of integration. Those are the easiest type over a rectangular region. But it doesn't have to be. We had one over here where we had this little triangular region. And we defined that, we said x was between 0 and 1, but y was between 0 and the line 1 minus x. Well, you can put variable limits of integration in this. So y goes from 0 to 1 minus x. Let's see. And it can do most of these. Sometimes it'll come back and not be able to compute it. So x, y, e to the x, dy, dx. Y went from 0 to 1 minus x. This line here. And x goes from 0 to 1, and it gives this decimal 0.063. Okay, so we are going to actually get to those variable limits next week. But just to show you that this same TeX tool does do that, again, for now, we're always having constant limits of integration. Okay. All right, let me just a moment to summarize and then set up for next week. So at the end of week 1, we're about halfway through chapter 4 of journal 3, and we've learned how to approximate volume with double Riemann sums, which we can keep improving our accuracy as we just increase the number of rectangles that we use. We found a TeX tool that does that, and it shows a nice visualization, CalcPlot3D. And then we learned how to do exact volumes using letting the number of rectangular prisms that we're trying to use for approximate volume, as that goes to infinity, we'll get exact volume, and that actually is a double integral. And we're so far restricting ourselves to only look at rectangular regions. We learned a couple ways in which we can flip the order of integration. It doesn't matter whether you're dx dy or dy dx, so long as you have constant limits of integration. And you can use, for some of your problems for your homework, you can use Fubini's theorem, which is nice. You can take a double integral, and rather than working it from the inside out, you can work it as 2 single integrals multiplied together if you have a separable function. So practice that with your homework problems. It'll be fun to see which ones can be a little bit easier. Do these ones by hand, but then you can check your work with TeX tools like Symbolab's a good one. And I showed you Wolfram Alpha. Okay, have fun. And then next week, we're going to get to even more interesting regions over which we can evaluate volumes.